You think an atom is a tiny ball? Solid? Definite? Somewhere specific? Wrong. Every experiment since 1801 tells you atoms act like ripples spreading through space. Not sometimes, always. The ball picture breaks the moment you look close. Why do physicists still call them particles when the evidence screams wave? What happens when you fire one electron at two slits? Where does it actually go? And if it is a wave, what is waving? The story starts in 1801. Thomas Young at the Royal Institution in London. He cuts two narrow slits in a barrier, shines light through them, expects two bright strips on the screen behind, gets stripes instead, bright, dark, bright, dark, bright. An interference pattern. Water does this, sound does this, waves do this, not particles. Young proved light is a wave, and Isaac Newton was wrong about light being corpuscles. The scientific world accepted wave theory. For over a century, nobody questioned it. Discrete chunks of energy. The energy depends on frequency, not intensity. One photon with enough energy kicks out one electron. 1,000 low-energy photons do nothing. Einstein won the Nobel Prize in 1921 for this work, not for relativity, for proving light is also a particle. Both wrong if you think they are mutually exclusive. Louis de Broglie in 1924 made the leap. If light waves can act like particles, can particles act like waves? He calculated that every moving object has a wavelength. The formula ties together Planck's constant 6.626 times 10 to the negative 34 joule seconds, the object's momentum, and its wavelength. For a baseball, the wavelength is so tiny it does not matter. For an electron, the wavelength is comparable to atomic distances. Measurable. Testable. Documented in Nature Physics, published in 2025, and foundational quantum mechanics papers from the Chemistry LibreTexts database, updated in 2023, which compile peer-reviewed experimental results from institutions including MIT, Griffith University, and the University of Innsbruck. Now back to the information. They fired electrons at a nickel crystal. If electrons are particles, they scatter randomly. If electrons are waves, they should diffract, create an interference pattern. They got the pattern. Bright and dark bands, just like light through a double slit. The spacing matched de Broglie's predicted wavelength exactly. That same year, George Thomson, son of the man who discovered electrons are particles, fired electrons through thin metal foils. Got diffraction rings, circles of light and dark, unmistakable wave behavior. Davison and Thomson shared the Nobel Prize in 1937. One generation proves electrons are particles. Next generation proves they are waves. Both correct. Fired a beam of 40 kilo electron volt electrons at them. Got an interference pattern. Electrons acting like waves. Not new. The experiment had been done. But technology was not good enough yet to fire one electron at a time. That came in 1974. Pier Giorgio Merli, Gianfranco Misseroli, and Giulio Pozzi at the University of Bologna. They used an electron biprism to split the electron beam. Reduced the intensity so low that only one electron existed in the apparatus at any moment. Filmed the results. At first, individual dots appeared randomly on the detector screen. One electron, one dot. Particle behavior. But as more electrons arrived, the dots accumulated into the striped interference pattern. Each electron went through as a wave, arrived as a particle, interfered with itself. Akira Tonomura and colleagues at Hitachi in 1989 repeated this with even better control. They needed the electron source, the biprism, and the detection system to remain stable for over 20 minutes while the pattern built up. The fringes formed gradually, electron by electron, no two electrons in the system simultaneously, yet the wave pattern emerged. Each electron knew about both slits, even though it arrived as a single point. Richard Feynman called this the central mystery of quantum mechanics. He said it contains the only mystery, everything else is commentary. The lower energy meant longer de Broglie wavelength, wider fringe spacing. They could close either slit independently with a mask. They detected 1 electron per second. Probability of 2 electrons in the system simultaneously was less than 0.999999%. They ran the experiment for 2 hours. The interference pattern emerged. Perfect. Undeniable. Published in New Journal of Physics. Each electron is a wave when traveling, a particle when detected, both always. Published in Reviews of Modern Physics. Neutrons have mass, 939 times the electron mass. Still showed interference. In 1998, Gerhard Rempe's group at the Max Planck Institute used atoms in an interferometer. In 2011, Stefan Gerlich and colleagues at the University of Vienna put molecules through a double slit. Not small molecules, phthalocyanine molecules, 48 atoms each. Then they tried fullerenes, carbon-60 molecules with 60 atoms, interference pattern, then C70 with 70 carbon atoms. Still worked. In 2012, they published results in Nature Communications showing interference with molecules containing up to 430 atoms. Total mass 25,000 daltons. These are not quantum oddities. These are complex molecules, hundreds of chemical bonds. They still act as waves. The double slit experiment scales up. The bigger the object, the shorter the de Broglie wavelength. Eventually you hit practical limits, but the principle holds. Everything is a wave. When you try to detect which slit the electron goes through, the interference pattern vanishes. Not fades, vanishes. You get two strips, particle behavior. This is not a matter of clumsy detectors disturbing the electron. In 2025, a team at MIT led by Wolfgang Ketterle performed the most idealized version of the experiment to date. They used single atoms and single photons. They measured how much information they extracted about the photon's path. The more path information they obtained, the more the interference pattern degraded. Perfect correlation. Published in Physical Review Letters. Niels Bohr and Albert Einstein debated this in 1927. Einstein thought you could measure which slit without destroying interference. Bohr said no. Measurement collapses the wave. You get either wave behavior or particle behavior. Never both simultaneously in the same measurement. Bohr was right. Every experiment since confirms it. But from outside, until Wigner opens the door, the friend and the measurement exist in superposition. Both measured and not measured. The new experiments used photon polarization and entanglement. They showed that what the friend experiences depends on how Wigner chooses to observe later. No absolute reality, only relationships between observers and systems, makes you question what is real. But we have more evidence that particles are waves at their core. Heisenberg's uncertainty principle. Werner Heisenberg proposed it in 1927. You cannot simultaneously know a particle's exact position and exact momentum. The more precisely you measure one, the less precisely you can know the other. This is not a technical limitation, not bad equipment. It is fundamental to nature, the product of position uncertainty and momentum. Uncertainty must be at least Planck's constant divided by 4 pi, around 5.27 times 10 to the negative 35 joule seconds, for an electron confined to 1 micrometer. The velocity uncertainty is at least 57.9 meters per second. Not because your detector is clumsy, because the electron is a wave. Waves are spread out, not localized. Earl Hesse Kennard derived the mathematical relationship in 1927. Hermann Weyl refined it in 1928. The inequality has been tested extensively. In 2016, a team at the University of Science and Technology of China, led by Professor Zhongfeng Du, verified Heisenberg's original measurement uncertainty principle using nuclear spin qubits, published in Physical Review Letters. They measured compatible observables that approximate incompatible ones, like position and momentum, showed the trade-off. Smaller measurement error means larger disturbance, confirmed quantitatively. In 2011, Li Chuanfeng and colleagues at the same university tested the entropic uncertainty relation with quantum memory, published in Nature Physics. They used entangled photons, showed that when a particle is entangled with a quantum memory, the uncertainty is reduced. With maximum entanglement, you can predict measurement outcomes perfectly. The principle holds, but can be beaten with quantum tricks. Published in Nature Physics on January 10, 2025. They confirmed a 2014 theoretical prediction. Measurement uncertainty and wave-particle duality are equivalent, not two separate mysteries, one phenomenon. The more you know about which path the particle took, its particle nature, the less you see interference, its wave nature. The sum is constant, a trade-off built into reality. Fullerene molecules were tested for uncertainty in 2001. Olaf Nares, Marcus Arndt, and Anton Zeilinger heated C70 molecules to 900 Kelvin. Hot molecules. They passed them through a narrow slit and measured the diffraction pattern. The slit width times the momentum spread equaled Planck's constant. Direct verification. Molecules at high temperatures still obey quantum rules. Published in the archive in May 2001. The wave nature persists. Heat does not destroy it, even for complex objects. In Light Science and Applications in January 2023, from Chinese research teams verifying quantum Cheshire cat separations at the fundamental level. Now back to the information. That ripple is what we call an electron, same for photons. The electromagnetic field pervades space, a photon is an excitation, a quantum of the field. This framework emerged between 1928 and 1930. Pascual Jordan, Eugene Wigner, Werner Heisenberg, Wolfgang Pauli, and Enrico Fermi developed it. They realized that just as photons are excited, states of the electromagnetic field, electrons are excited, states of the electron field. Protons have a proton field. Quarks have quark fields. Every particle type corresponds to a field. The particle is what you observe when you poke the field hard enough. Think of it like a drumhead. The drumhead is the field. Hit it and you get a vibration. That vibration travels, carries energy, looks localized. You might call it a particle, but it is fundamentally a wave in the drum. A probability distribution, The wave function evolves according to the Schrödinger equation. When you measure, you collapse the wave function to a definite state. Before measurement, the particle is everywhere. The wave function is non-zero. Not that you do not know where it is. It genuinely is in all those places simultaneously. This is superposition, demonstrated experimentally countless times. In 2025, researchers in Austria demonstrated superposition at record temperatures. Gerhard Kirchmayer's team at the University of Innsbruck created Schrödinger cat states, quantum superpositions of opposite states, at 1.8 Kelvin, published in Science Advances, April 4, 2025. This is 60 times hotter than the surrounding environment. Previous experiments required near absolute zero, ground state cooling. The Innsbruck team started with a thermally excited state, a hot state, still achieved superposition. They used transmon qubits inside microwave resonators, applied two protocols, echoed conditional displacement and quantum coherent mapping. Both produced hot cat states. The Wigner function showed negative values, quantum signature, interference patterns at high temperature. Thomas Agrinius, one of the researchers, said colleagues were surprised. Temperature usually destroys quantum effects, but interference persists, even when hot. 0.58 for bipartite cat systems. But the principle is proven. Quantum effects are robust. Superposition survives heat. He thought it proved quantum mechanics was incomplete. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published the EPR paper. They argued that quantum mechanics could not be the full story. Hidden variables must exist, deterministic properties the particles carry. John Bell in 1964 derived an inequality that local hidden variable theories must obey. Experiments can test Bell's inequality. Alain Aspect in Paris in 1982 did the first convincing test. Violated Bell's inequality, no local hidden variables. Quantum mechanics is complete, or reality is non-local, or both. Chose measurement settings faster than light could travel between the stations. Violated Bell's inequality by many standard deviations. No local realism. The particles do not have definite properties before measurement. The wave function is real, or at least no classical explanation works. Schrödinger cat states involving multiple photonic modes, up to 4 modes entangled. Full quantum state tomography confirmed entanglement. They achieve this using superconducting qubits in microwave cavities. The qubit reflects coherent state microwave pulses. Each reflection creates entanglement with another photonic mode. Scale it up, and you get a multipartite cat. Flying cat states. Itinerant photons in superposition and entangled. The paper measured negativity, a quantum entanglement measure, of 0.192 for single-party systems and 0.135 for bipartite systems. Positive values mean entanglement exists. Verified. They showed that wave behavior, particle behavior, and entanglement are not separate. They are connected by conservation laws. When one increases, others decrease. Total quantum coherence is conserved. They verified this using silicon-integrated nanophotonic quantum chips. High-dimensional systems. The experiments confirmed the theory. Wave-particle duality is not a standalone mystery. It is part of a larger framework involving entanglement and quantum information. The team prepared pre-selected and post-selected states of single photons, used weak measurement, extracted weak values of different operators. The results showed wave and particle attributes spatially separated. The photon's wave nature was in one location, its particle nature in another, simultaneously. This is not just a theoretical curiosity. It shows that wave and particle are not inherent to the object. They are relational. Depend on how you prepare and measure. That is what interferes, that is what collapses when you measure. For 2 entangled particles, it is a wave in 6-dimensional space. 3 dimensions for each particle. For n particles, 3 n dimensions. Not physical space, an abstract mathematical space. The wave function lives there. When you measure, you collapse that 6-dimensional wave to a definite configuration. A point in the configuration space. That point corresponds to definite positions in physical space for both electrons. But before measurement, the wave is spread out in 6 dimensions. Interference happens in that abstract space, not in the 3-dimensional space you see. The many worlds interpretation says the wave function never collapses. It keeps evolving. Measurement splits the universe into branches. Each outcome happens in a different branch. You only see one outcome because you are in one branch. Other branches exist but are inaccessible. This interpretation takes the wave function literally. No collapse, no measurement problem. Just unitary evolution and branching. It is mathematically consistent. Philosophically controversial. No experimental test distinguishes it from other interpretations, yet. This reproduces all quantum predictions, but it requires instantaneous action at a distance, non-locality, and the particle's position is hidden. You cannot measure it without disturbing the wave. So operationally, it is identical to standard quantum mechanics, Different ontology, same predictions. Not a physical thing. The particle has properties only when measured. Before measurement, asking where the electron is makes no sense. The question is meaningless. Measurement creates reality. This interpretation dominated for decades. But it leaves the measurement problem unresolved. What counts as a measurement? Where is the boundary between quantum and classical? No clear answer. Quantum Bayesianism, or cubism, says the wave function represents an observer's knowledge, not objective reality. When you measure, you update your knowledge. The collapse is subjective. Different observers can have different wave functions for the same system. All valid. This interpretation makes quantum mechanics a theory of information, not of matter. It resolves many paradoxes, but it seems to deny objective reality. Hard to accept for many physicists. Frequent for large systems. This explains why macroscopic objects do not show superposition. Testable. Experiments are underway. Nothing found yet, but the search continues. The double-slit experiment works with molecules of 2,000 atoms. Interference survives, heat up to 900 Kelvin. Entanglement links particles across kilometers. Superposition persists even in noisy environments. They do not have definite positions until measured, and they do not follow definite paths. The path is the wave function, a superposition of all possible paths. Feynman's path integral formulation makes this explicit. A particle going from A to B takes every possible path simultaneously. Each path contributes a probability amplitude. Add them up, square the result. You get the probability of detection at B. This is not metaphor. This is how quantum mechanics calculates every path, every route, simultaneously. The vector potential, not the field, is fundamental. The electrons sense the potential along all paths. Classical particles could not do this. Waves can, confirmed in countless experiments since. The act of gaining path information, particle-like knowledge, destroyed the wave-like interference. Complementarity. You choose what to measure. Nature shows you that aspect. Measure position. See a particle. Measure momentum spread. See a wave. Never both. In this setup, you decide whether to measure which path information or observe interference after the photon has already passed through the slits. Classically, this should not matter. The photon already took one path or both before you chose. Quantum mechanically, your choice retroactively determines whether it behaved as a wave or particle. The experiment confirmed this. The photon adapted to your choice. Not because the choice went backward in time, because the photon was in superposition until measured. Your measurement choice selected which aspect of the superposition you observed. He said, both are classical concepts that do not fully describe quantum reality. The quantum world is not made of waves or particles. It is made of something else, something that exhibits wave properties in some experiments, particle properties in others, but is neither. But the distribution of those dots, accumulated over many trials, shows wave interference. The wave-like behavior is reconstructed from particle-like observations. You never see a smeared-out matter wave directly. You see individual clicks. But those clicks form a pattern only explicable by wave interference. This is the essence of quantum mechanics, particle-like detection, wave-like propagation, both true, both necessary. Quantum field theory resolves the paradox by making fields fundamental. Particles are excitations, ripples. The field is always there, spread through space. When energy is high enough at a location, you detect a particle, a localized excitation. But the excitation arose from a wave-like disturbance in the field. The two pictures merge. Particles emerge from fields. Fields produce particles. Both aspects are real, both part of the same entity. And this is not just electrons and photons. Protons are made of quarks and gluons. Quarks have quark fields. Gluons have gluon fields. Quantum chromodynamics describes this. The fields obey wave equations. Excitations are quarks and gluons. Those excitations propagate, interfere, entangle. Protons themselves are composite. But at the fundamental level, everything is field excitations, ripples in the quantum fields that fill the universe. Recent observations from cosmology support this. The cosmic microwave background shows tiny temperature variations, 1 part in 100,000. These variations are believed to originate from quantum fluctuations in the inflatant field during cosmic inflation. Subatomic quantum fluctuations blown up to cosmic scales, imprinted on the universe, observed by the WMAP satellite and later by Planck, the seeds of galaxies. Structure in the universe, all from quantum field fluctuations, ripples in a field, amplified, frozen into the fabric of space. This is not speculation. This is the standard model of cosmology, backed by data. Verified, confirmed in thousands of experiments over more than a century. You can see the interference, you can calculate the probabilities, but you cannot see both wave and particle simultaneously. Complementarity forbids it. Nature gives you one or the other. Your choice of measurement determines which. Not because nature is playing tricks, because nature is quantum, the wave function is fundamental. The particle is what you observe when you collapse the wave. Every experiment since Young's double slit in 1801, through Einstein's photoelectric effect in 1905, de Broglie's hypothesis in 1924, Davison-Germer diffraction in 1927, Heisenberg's uncertainty in 1927, Feynman's path integrals in 1948, Aspect's Bell tests in 1982, Tanimura's single electron interference in 1989, delayed choice experiments in 2012, fullerene interference in 2011, hot Schrödinger cats in 2025, wave particle conservation laws in 2025. Every result points the same way. Atoms are waves. Joachim Argelander and Daniel Spegel-Lexna at Linköping University in Sweden, working with collaborators in Spain, used orbital angular momentum states of light. They measured path information, particle aspect, and interference visibility, wave aspect. Found a precise trade-off. More path information means less interference visibility. The relationship is quantitative. Entropic uncertainty equals wave-particle duality, one phenomenon. Two descriptions. The paper in Physics World on January 10, 2025, confirmed a 2014 theoretical prediction by Patrick Coles. Physicist Jonas Mazzero in Brazil called the experiment innovative and precise. The result applies to distinguishability-based complementarity relations, not all cases, but it is a major step. Uncertainty and duality are not separate mysteries. They are the same thing. Measurement of one property limits knowledge of the complementary property. This is baked into the structure of quantum mechanics. George Gamow explained this in 1928. Gerd Binnig and Heinrich Rohrer invented the scanning tunneling microscope in 1981. Electrons tunnel from tip to surface, won Nobel Prize, 1986. Images show individual atoms, electrons as waves leaking through vacuum. Ammonia molecules tunnel. Nitrogen atom tunnels through the hydrogen plane, 24 gigahertz oscillation. Ammonia maser, built 1954, first maser, works because molecules are waves. Enzymes use proton tunneling, speeds reactions by thousands. DNA replication involves tunneling. Mutations from quantum effects, ribosomes use tunneling for peptide bonds. Quantum effects at room temperature in biology. Wave function matters for life. About half the quantum of energy for a harmonic oscillator, measurable. This is direct evidence of quantum motion at zero temperature. Ball model says everything should freeze solid. Wave model says motion persists. Helium agrees with wave model. Electrons and atoms have zero-point orbital motion. The Bohr model tried to fix this by saying electrons orbit like planets. Wrong. Wave mechanics says the electron is in a standing wave around the nucleus, the ground state orbital. One wavelength fits around the circumference for the lowest angular momentum. Half a wavelength radially for the lowest radial state. The wave never stops, always moving, always spreading, always quantum. The Casimir effect proves zero-point energy is real. Hendrik Casimir predicted in 1948 that two uncharged metal plates in vacuum attract each other. Why? Quantum fluctuations of the electromagnetic field, virtual photons. Between the plates, only certain wavelengths fit. Outside, all wavelengths exist. Pressure difference. The plates attract. The force is tiny, inversely proportional to the fourth power of separation, but measurable. Steve Lamoureux at the University of Washington measured it in 1997. Force matched Casimir's prediction. Quantum vacuum is not empty. It seethes with virtual particles, ripples in fields, constantly appearing and disappearing, energy borrowed from uncertainty, paid back before anyone notices. Published in Physical Review Letters in 2005, measured at separations down to 100 nanometers. Matches theory. Quantum electrodynamics predicts the effect. Experiments verify. The vacuum is full of zero-point fluctuations. Electromagnetic waves with no photons present, waves in the field itself, ripples in the quantum field even when empty. This makes no sense if photons are particles. Makes perfect sense if photons are field excitations. Waves in the electromagnetic field. Always there, always fluctuating. The Dirac equation, formulated by Paul Dirac in 1928, describes relativistic spin-half particles. The equation naturally produces spin, not put in by hand, emerges from the mathematics. Spin is a consequence of the wave nature combined with relativity. The electron wave function has four components, 2 for spin up, 2 for spin down. The wave carries spin, not the particle, the wave. Electrons in a magnetic field split into two energy levels. Zeeman effect, measured spectroscopically. The energy difference depends on spin. Explains the fine structure of atomic spectra. Otto Stern and Walther Gerlach in 1922 passed silver atoms through an inhomogeneous magnetic field. atoms deflected, not smoothly, two discrete spots, spin up, spin down, quantized. Only those two values, not a continuum. This is the Stern-Gerlach experiment, foundation of quantum mechanics, proves angular momentum is quantized, proves spin is real, proves particles are quantum objects. One down. This determines the periodic table, chemical properties, bonding, everything. All from spin, all from the wave nature. The wave function of two identical fermions is antisymmetric. Swap the particles. Wave function changes sign. This is why two electrons with the same spin repel more than classical repulsion predicts. Exchange interaction, quantum effect, ripples in the electron field. Symmetric wave functions, or they can occupy the same state. Bose-Einstein condensation, predicted in 1924, observed in 1995. Cornell, Wyman, and Kettle cooled rubidium atoms to billionths of a degree above zero. The atoms condensed into a single quantum state, a macroscopic matter wave. Thousands of atoms as one wave. Published in Science, 1997. Two condensates overlap, form interference fringes. Matter waves interfering. Josephson effect, predicted by Brian Josephson in 1962 while he was a graduate student, measured shortly after, won him the Nobel Prize in 1973. Superconducting quantum interference devices, SQUIDs, use this effect. Most sensitive magnetic field detectors measure fields down to femtoteslas, medical imaging, geophysics, fundamental physics, all based on electron waves interfering. Helium-4 below 2.17. Kelvin becomes a superfluid, flows without viscosity. The atoms form a Bose-Einstein condensate, a macroscopic quantum wave. Helium-3 at millikelvin also goes superfluid through atom pairing. Multiple exotic phases, proof that quantum waves dominate even complex systems. If particles are balls, they should bounce or stick. They do not. They annihilate. Create new particles, quarks, gluons, leptons, bosons. Energy becomes particles. Particles become energy. Mass is energy. Einstein's E equals mc squared. But more than that, the new particles emerge from the collision region, not from the incoming particles, from the fields, the electromagnetic field, the quark fields, the lepton fields. High energy excites the fields, creates ripples. Those ripples are particles. They spray out, detected in calorimeters, trackers, measure momentum, energy, identity. Every collision is different, quantum randomness, but statistical patterns emerge, cross-sections, decay rates, all predicted by quantum field theory, all measured, all agree. The Large Hadron Collider collided protons at 14 trillion electron volts, center of mass energy, enough to excite the Higgs field, create a Higgs boson. The boson is unstable, decays in 10 to the negative 22 seconds, before traveling a distance, no track, only decay products, 2 photons, 4 leptons, 2 Z bosons, multiple channels, ATLAS and CMS collaborations. Combined data, saw a peak at 125 gigaelectron volts, 5 sigma significance. Discovery, the Higgs field exists, the boson is its quantum, a ripple in the Higgs field, predicted in 1964, observed 48 years later. Quantum field theory works. The fields are primary, the particles are secondary. Exchange a photon, transfer momentum, feel a force. But the photon is virtual, borrowed from uncertainty, exists for a brief time, mediates interaction, disappears. The electromagnetic field ripples. The ripple pushes, charges apart, or pulls them together. Not billiard balls bouncing, fields interacting through quanta, ripples exchanging momentum. Electrons shared, electrostatic attraction, but mediated by photon exchange. Virtual photons, constantly emitted and absorbed. The electrons in one atom interact with the nucleus of another. Photons carry the interaction. The electron clouds overlap, interfere, form molecular orbitals, standing waves around both nuclei. The molecule is a single quantum object, a wave function spanning multiple atoms, not individual balls orbiting. A distributed wave, a ripple in the electron field shaped by the nuclear potentials. But experiments say otherwise. Aspect in 1982. Ways in 1998, Rowe in 2001, Salert in 2008, Justina in 2013, Henson in 2015. Each experiment closed loopholes. Detection loophole, locality loophole, freedom of choice loophole, all closed, Bell inequality violated, no local hidden variables. Quantum mechanics is correct, or locality is violated, or both. Most physicists accept non-locality. Entangled particles form a single wave function, even across kilometers. Measure 1, collapse is instant. The other responds. Not because a signal travels, because they are one quantum system, one ripple in the combined field, Distance does not separate them in the wave function space. But entanglement-based protocols are more robust. Eckert protocol. Entangle 2 photons. Send one to Alice, one to Bob, measure polarizations. If an eavesdropper intercepts, the correlations degrade. Alice and Bob detect tampering. Secure communication guaranteed by quantum mechanics. No mathematical assumption, physical law. The wave function cannot be cloned. The no-cloning theorem, proven by Wouters and Zurich in 1982. Consequence of linearity. Quantum information is different from classical, cannot copy without destroying, cannot measure without disturbing. These are not technical limits, fundamental. Google in 2019 demonstrated quantum advantage with their Sycamore processor. The technology works because atoms are ripples, quantum waves that interfere, compute in parallel through quantum superposition. The wave function explores all paths simultaneously. Complex amplitudes. Square them, get real probabilities. The wave function evolves according to Schrödinger's equation. Measurement collapses it. This formulation works perfectly, predicts everything. Multiple interpretations exist. Many worlds, pilot wave, Copenhagen, cubism. No experiment distinguishes them yet, maybe never. What matters are the predictions, and those are clear. Particles behave as waves. Interference proves it. Tunneling proves it. Entanglement proves it. Zero-point energy proves it. Spin proves it. Quantum field theory proves it. Every experiment for 125 years proves it. They have zero-point motion. They form condensates. They pair in superconductors and superfluids. They exist in quantum superposition even at high temperatures. They violate Bell inequalities. They enable quantum computing. They mediate forces through virtual quanta. They are excited states of underlying fields. They are quantum, and every experiment confirms it. The ball picture is dead. The ripple picture is reality.